Yeah. Yeah, now it's good. Yeah, very nice. Yeah.
suitable for visualization. Okay, maybe these x's, these are data points for size versus price. Okay, so this point is in a Euclidean geometry, or you can say in a Cartesian coordinate. If you are telling this point with the x and y coordinate, then it is a Cartesian coordinate. If you are telling this with terms of a vector, then it is in Euclidean geometry, like that. I just wanted to say how Euclidean geometry and Cartesian coordinates are used in terminologies. Am I clear? I don't know if I'm very if my things are very clear to you.
But this is very
Yeah,
interesting.
yeah,
So, go on, Paul.
yes, yeah, yeah. So one question, like Cartesian coordinates, I'm clear. Like x and y-axis data will and merge into some point. But
Hmm.
what is Euclidean?
Hmm.
This one? Uh,
Euclidean geometry. Euclidean
yeah,
geometry. Yes.
yeah.
So
What is that?
Cartesian coordinate x y. You say with x y coordinates you can define a point over a plane.
Yeah,
But Euclidean, what you say Euclidean? A vector. Okay. Suppose I have this. Can I draw here? Yes, I can draw here. Right. I have a pen. Okay. So this point I want to mention, okay, with Euclidean geometry. How will I describe this point? I will take a line from origin. This origin can be anything, okay. It is not fixed, like, okay, the 0 0 will have to be used. You can use any frame of reference. You can use any frame within the universe. You can use any frame within your room. You can use any frame within your city, okay. So with respect to one origin, you draw a line to that point, okay. Then it is a vector because it has a length and it has a direction, okay. So when we talk about Cartesian coordinate, we say x and y. In terms of Euclidean geometry, we will write like this. In terms of vector, what will say for this is 2 dimension. I will write this as x and I will write this as y. This will define my vector here. So this is Euclidean geometry. It is the same thing represented in a different way. If it was 3 dimensional, then the dimension would be intuitive, right? You can say this right now. It will be x, y, and z. Okay. So what we will call this vector? This vector lies in like this. In mathematical foundation of data science, we have learned like this. We used to write like this, no? R3
yeah, yeah.
in 3 dimension. This denotes 3 dimension, and this one is in capital 2, like it is in 2 dimension. Similarly, if I have a data set, typically we see data sets like rows and columns, right? So if there is a data set, suppose there are m columns and m rows and n columns, then what does it mean? It means that the dimension, the column space, like this column, this represents 1 dimension, say this x. This column, say, represents another axis, x2. Okay. This column represent another axis, say here, x3. Okay. So these columns are m-dimensional. M M-dimensional. Okay. And there are like row space. These are the rows. These are n-dimensional. Okay.
So this is what we know about Cartesian and Euclidean geometry. Why am I telling you this? Because I had very hard time in understanding how do they how do they even start to visualize the hypothesis space. You must have seen they are using um, Gaussian function for probabilistic distribution, right? Which is an invert the bell-shaped curve, and for this
Normal distribution.
yes, you can say normal distribution. It is Gaussian divided by root 2 pi, because they had to make the area under the curve equal to 1, and it is, and since that very equation, that the very function is not a closed form function, you cannot integrate that function. It is open ended, it doesn't end, and they don't even know how to end it, and they don't know how to even integrate over that. So they found out in a three-dimensional way that okay, the area under the curve will be under root 2 pi, like this function. No, this is not really a normal distribution. Okay, this is Gaussian distribution. You can write it like this: e raised to the power, sorry, if it is exponent, then it is of something minus of something square. This will give this inverted bell shaped curve. Okay, but how do I begin to get the area under the curve? How do I get the probability? For that reason, they found out that okay, we will have to divide it, we will have to normalize it, and to normalize it, they visualized it in 3 dimensions. And when they visualized in 3 dimensions, so by operating it layer by layer, you will find, have you guys heard about that channel 3 blue 1 brown, or 3 brown 1 blue? I don't remember the name exactly. Have you heard about
Yes.
it? So in that website, not the YouTube channel, but in the website, you will find there is a very good video. They explained every step on how this area was found. Okay, I will suggest after this video, I will after this session, I will share that video link with you guys, so you can see how they found the area under the curve, and they divided it with root 2 pi, so that it can be normalized to 1. Okay, so not deviating from the topic now. Yeah, so the decision tree was something like that. When I said Cartesian merged both the fields of mathematics, Claude Shannon is another mathematician or inventor of that time. I don't remember the year as well, but he was the guy who gave the information theory. Okay, so when we read about decision tree in the first semester in the data mining subject, we heard about this information gain ratio. Okay, so whichever feature gave us the more purity in the output target, we used to pick that. And even now, we are using the decision tree. The same ID3 algorithm is still being used, right? ID3, C4.5, then decision tree algorithms were now evolved. So we are still using this same principle. We find that very feature that gives us the most information out of the data set. And why do I say gives the most information? Because the output class is more pure. There is least error when you separate the data on that feature. Okay, so this is about decision tree. Support vector machine is also very old. We produce a margin to the entire decision boundary, so that we can be confident of Mm, Do you have to say something? Hello? Okay, okay, okay. So he must have joined now. Nah? I was not watching the screen. Okay. So Devdashi. Okay. So support vector machine, then naive Bayes algorithm. This naive Bayes algorithm purely based on probabilistic. There are two theories, two schools of probabilities. I hope you guys know about that. Can you say yes or no? There are two schools of thoughts for probability.
One is your empiricist thought, school of thought, right?
Which one?
By experimentation, right? You're talking
Oh,
about probability, right?
yes, yes, probability, yes.
So one is your uh, which you do by doing experiments, right? And another is
One
more
is by
theoretical,
imperative and one is by intuitive.
not
Oh,
intuitive actually, but one is by experimentation and one is a priori. Is that what you're saying?
yes, you're correct. I think the name goes by frequentist
Yes.
school of thought, and then is just Bayes school of thought,
Ha. Frequent.
right?
Frequent.
Mhm. So this experiment one is the frequentist one, and this Bayes one is based on evidence. They take that frequentist thought and then they see the evidence and then they improve upon the probability. Yeah, this one. Hmm. So after that, there is KNN. KNN is again what you say unsupervised learning. You give the data and see which data is near about. You cluster them together. Okay. So we have recently done our what we called it responsibility matrix. No, in GMM, Gaussian mixture models, we use that KMM algorithm where we've calculated expectation, then we calculated that matrix and all. So given that KNN algorithm again gives an intuition that okay, whichever data that you see existing in a plane or in a hypothesis space may or may not belong to a particular class, you have a probability that this particular data point might belong to uh, just a moment, where was this? Mhm. Do I have this here somewhere? No. Mhm. I don't have it here. Okay. Are we still there? Okay. So sorry, I don't have that slide. I will search for it and I'll share that intuition again. Okay. For KNN, I will note it down somewhere. Okay. So KNN is basically clustering based on the nearness of two data, three data, four data. Okay. K means is again the same. It can be K means and there are K medoid, uh, some other algorithms were there. I forgot the name right now. But all these are unsupervised learning. Okay. A random forest is like decision trees and lots of decision trees. It will start from one splitting point to other splitting point for continuous, for discrete variables, everything it will take, and then it will find out the better classes, which one is classifying the output target well. This one particularly I have used in the last few days for one classification problem. The random forest took the Jupyter notebook. The model size was hardly the Jupyter notebook file size was hardly 1.39 MB. By the time I could prepare the model, the Jupyter notebook would not even open. It was 23 MBs. The model was so heavy. I don't know how they make it in production, but this is very heavy random forest. Then we have dimension reduction algorithm. This, guys, I think this is very critical and this is very deep because I'm still reading all the topics for dimension reduction techniques and dimension reduction algorithm. And the part where I started about metrics, when you have identically independent features where you have to find inverse of that. If you cannot have a feature which are like independent, then the inverse is not possible, but yes, you can use pseudo inverse. So that very principle is applied here. Eigenvectors, eigenvalues, SVDs, and then what we have is something like QR technique is also there, no? Can anyone support on this? If anyone remembers, there's one decomposition technique for QR decomposition or something like that. Hello?
Not sure when it comes to dimensionality reduction, we just aware PCA, those kind of things.
Yeah, PCA is like using of eigenvectors. PCA is just that. We take out eigenvectors and eigenvalues when we use principal component analysis. Anyways, these topics are so very overwhelming. If I don't put notes, like having a session formally is very awkward. So let's start with the actual topic which I needed to share today. So regularization. First of all, it is lasso L1. Okay, then it is ridge regression, and this ordinary least squares is nothing but the linear regression, OLS. What it does is when we see that cost function, no, that hypothesis function where it is said W naught plus summation of 1 to n, summation 1 to n Wi into xi. When we see this, no, so this W0 is basically merged in ordinary least squares. When we use it in sklearn, what it does is it will do summation from summation will be done from I equal to 0 to n. Okay, and this W0 is gone. If we have to keep W0 here, then it is I 1 to n. That's the trick they use. So what is that trick? In actual computation, when we are in Python, here we have these columns, these features, right? X1, X2, X3. It will add another column to it in the beginning, and it will put all these values as 1. Okay, so ordinary least squares will add a column and it will add all these to 1, and then it will add this W0 to this one. Okay, so this is the intuition. Now what we have here is lasso. Lasso is L1. Lasso is least absolute shrinkage and selective something, right? About this in lasso was I keep on forgetting where I kept those ML merge lectures. Lasso. We have it here. Was it like that? Oh, I did not see. I have crossed my time.
I think Manoj, it's okay if Prasoon is going on. It's fine. I'll probably take sometime around 10 o'clock. Prasoon, I think you can talk
Can
about
you
it
hear me?
next 15-20 minutes, right?
Yeah, sure, sure. I've not even started. I was just building up that intuition because I did not know whether you guys are ready with the previous session things or not. That's why.
Please go ahead.
Okay,
I can
thank
chip in later. Is it okay, Manoj? No, it's fine. It's fine.
you. Okay, so this lasso technique, whenever you are told to explain lasso, please do remember this full form: least absolute shrinkage and selection operator. This is very crucial, and you will never forget why it is used. Lasso is the Manhattan distance. Lasso is the L1 norm. Lasso is the one which helps you to select the features in any data set. If you are using principal component analysis, you are good. If you are using decision tree to identify the best features, you are good. But if you are using lasso regression, then your half of the job is done. You don't even have to go to PCA. You don't even have to go to smart techniques to identify the features. It will do the job for you, and it will do the job behind the scenes. You won't even recognize. It will diminish all those features which are not required in your output. Okay, so please just rote learn the full form. You might save yourself from any question that is asked to you regarding regularization. So least absolute shrinkage and selection operator. Selection operator here says that it will select the features for you. Least absolute shrinkage tells you that this very L1 norm will give the very best feature with optimal weight. It will not unnecessarily magnify those weights, and it will not perform any underfitting for the smaller weights. If you say, if during the iteration uh, of a cost function, you remember the cost function, right? Or should I write it here? uh, there is this PPT. Okay, so we have a cost function. This is a model. This is a linear regression model. Okay, and this is a function, objective function. We have to do this. What is this? Can you guys tell me if you guys know, or should I explain about this function?
You mean the second one, right? Fixed rate optimize objective function.
Yes, I am asking about this one. This zero one loss function. Do you guys know what this one means before this bracket?
Uh, no, no.
Okay, so this is a zero one loss function, and this one is not related to zero one. This is simply an integer function in mathematics. The integer function gives you the integer. That's all. If the y, this is a prediction level. Yeah. So this, what is happening? So if this y is our target variable, this is our predicted variable. Okay, this is predicted y hat. This is predicted. Okay, so if these are same, this will give me 0. If these are different, say any values, it should be different. If it is 1, if it is pointed, it is different, it will give me the value 1. Simply output 1. This is the integer function. Okay, so I have tried to write down here as well. This is a 0 1 loss function, rounding every output to 1 if the label, this is the label, y is label, and this is predicted. If these are not equal, this will give me 1, and then we will sum it up. So basically we are summing up the errors. So I think it is clear right now, because if there is no error, there is no point of counting it, and if there is an error, we will count it. If there are 25 errors, it will sum it up to 25. Okay, and then we have our learning algorithm. Learning algorithm, what does it say? We cannot change the data, of course. We cannot change the output target, of course. But what we can change is the weight. We can change the bias, the B. Okay, we can change the bias, we can update it, and we can change the bias. So what we will do, we will find the best argument for W and B, which will minimize my error function. Suppose it is 25 right now. In the next iteration, it will be 23. In next iteration, then it will be 20. So on so forth, we will bring it down to minimal, say 10, 11, or 12. Okay, just to generalize the model. So these are these loss functions. This is the 0 1 loss function which I mentioned, which we saw here earlier in that slide. This is a Heinz function. What is a Heinz function? It will give you either 0 or 1 minus y1 dash. Okay, y is the label, y dash is the predicted value. Okay, so y1, out of y1, it will give me, and then you will subtract it from 1. Whichever value is higher, it will give you. Suppose this value is greater than 1. If this value is greater than 1, it will give you that value, say 0.5. It comes out 0.5, it will give you 0.5. If it is minus 0.5, it will give you 0. So Heinz loss, you can tell like a ReLU function, maybe. Can you see that? It will only give you either 0 or more than 0, right? Then we have our exponential loss function. What we will have here is, the exponential loss function will give you a curve like this. Getting the intuition right now? If it was plus sign there, the function would be like this. Okay, it is a convex function, but it will, just because it has minus sign over here, it will be a concave function. Okay, and then it is our famous squared loss. It is not the average squared loss, but the squared loss. In average, for when we use it in cost function, we average it with n, and then we also add this 2, because after differentiating we get the 2 here, which will cancel out. Okay, just to simplify our calculation, we use this as a cost function. So when we have all these loss functions, we select any one, and then we develop our learning algorithm. See, we are using this exponential. Say, for example, we are using this objective function, this loss function, and our learning algorithm is trying to minimize this. Okay. So what we will actually do, we will start iterating. Since it is a convex function, we will start iterating. We will see the loss. we will keep updating our weights. We keep updating, and once we reach the minima, we might overshoot ourselves. The function which is learning this will overshoot. This might overshoot, and this will end up here after some given threshold of iterations, say 1000 iteration. If we say we have given the model, okay, after 1000 iteration you stop, okay, then it will end up over here. It won't find the minima. It won't find the minimal loss. So what we will do, we will add our regularizer. Now, the main topic, why are we adding this regularizer, is because we need someone to tell it, don't overdo yourself. We don't want to overdo this minimization. If you are minimizing W more than what is required, I will add a penalty. How can I add a penalty in an equation? Is by giving you a constant. Okay, this is a constant lambda, which is called the regularizer parameter. Earlier we had this eta, which is a learning rate, right? So while using the stochastic gradient descent or gradient descent, we were using learning algorithm to update our weights. And how did we do that? This was the delta rule, where the weight, the final weight would be initial weight plus delta W, and the delta W was calculated by this dou J by dou W minus eta. Okay, I sorry, I don't have a pen for this. This writing is very poor. So it is basically minus eta dou J by dou W. Okay, so, and since this, we don't have one feature, there are several features. Every feature will have their own weights. So every weight will be updated using this delta W. So for first feature, it will have delta W1. Here we will be differentiating, partially differentiating with respect to delta W. I hope you guys remember that Hessian matrix and the part in MFDS where we did find, the second derivative, second order derivative. Do you guys remember it yet? Because I don't have the tools to explain it again. That's why I just want you guys to confirm. Hello, can someone just confirm?
Can you just repeat, Prasoon, what you asked? Second, you asking about the second derivative, is it?
Yeah, did you guys remember the Hessian matrix, the saddle point, second derivatives, etc.?
Yes, I mean intuitively, you see, first derivative will tell you about the speed, and second derivative will tell you about the acceleration, right?
Yes,
So, second derivative is actually how first derivative will tell you about the tangent, right?
correct.
The direction of tangent, and second derivative will tell you about how it is changing,
Yes,
how tangent is changing.
correct. And given the uh, feature that we are using for reference, it will tell you, like how you said, how you started. It will tell you it tell us the speed and then the acceleration. If we somehow were talking about distance with respect to time, it was once speed with the first derivative and then the acceleration with second derivative. But now with features like these weights, it will tell us about this hypothesis space, right? Consider this as a consider this in a third dimension, in three dimension. How it will look like? It will look like I don't know if it is visible correctly. uh, can you guys see this? Is it visible?
Yes, yes,
Okay,
yes.
so I had tried to make this two axes. One is W1, the other one is W2. You can call it by any other name. If you want to call it by theta, that is also okay. If you want to call it by beta, that is also okay. Many books, many lecturers, many YouTube videos use different notations, and it is very easy to get overwhelmed by these notations, which happened to me because I could not understand why in some books they mentioned like for the cost function. I know I told you na, for the cost function here, that 1 over 2n. In some books, they did not use 1 over n. They directly used 1 over 2. In some books, they did not use 1 over 2, but use 1 over n. So it is very easy to get overwhelmed and then confused by all these notations. So you can call it by any name, it would mean the same. Okay. And this function, this hypothesis space which we talk about, is nothing but the loss function. How the loss functions look like? It looks like this. This looks like an umbrella open upside down. Okay, so consider this as an umbrella. The stick is like this. Okay, this is an umbrella and this is upside down. We have here is weights. Okay, W1 and W2, it can call it by any other name. And this axis, my friends, this axis is J theta. You can call it JW, you can call it J simply. It is nothing but the error. This you can call it E as well. Okay, and no matter what you use, the surrogate loss function will look like this. Okay, so when we know the loss as this, certainly we will try to minimize the loss towards this direction. But since our algorithm, this is our algorithm, right? This is our learning algorithm. This algorithm, the shape of this algorithm is like this. How can I instruct this algorithm to find those arguments which take the values downwards? Can you even start to guess how it is happening? Like, I have a function which is like this. See, exponential minus this. The function shape is like this. The error shape is like this. How can I instruct my algorithm to find something which is down below here? I will have to come up with a separate set of algorithm to update this. Okay, so what do? I bring out gradient descent, and then I use another algorithm to update my learning algorithm. So my learning algorithm will remain always the same, whichever way I took it. Okay, I have to use gradient descent as a separate algorithm. So what is my gradient descent algorithm? It's very simply, this is the formula and this is how I update it. I have to take an random weight, initial weight, say 0. Okay, for practical purposes, we take 0. Then I will repeat until those weights are same, like they are not changing there. Okay, or maybe there is a threshold of iterations, say 10,000 iterations, and then stop. If you are not finding any minima, then it's okay. Just stop it where you are. Okay, so this I tried to just make it like in Excel. I started at like at 2 o'clock in the afternoon today. So these are two features, x1 and x2. Okay, these are just random values, and this is the target variable. Okay, y hat is the predicted variable, but it is 0. I don't have any intuition on how I can get to this value. Okay, but I know that this is a linear.
So can you zoom a bit so that things are a bit more visible?
Yeah, sure.
Yeah.
Thanks. So x1, x2 are the two features. Y is the target variable. Y hat is my predicted variable, which I have no clue about how to fit a line, how to fit a polynomial line. I don't have any clue. But I know that I want to use linear regression, correct? Now what I will do for linear regression, I always know the formula is y is equal to w I into x I. Okay. So this is the function for linear regression, plus not to forget the bias. Okay. So wi or m1, any way you call it, m1 is the slope, wi is the slope, you can call it by any name, it will just be the same. So I started with 0, just like how I said for the initial values, pick a starting point w, it can be anything, but for practical purposes we take 0. We took 0 and the resulting were 0. What to do now? We just take the error. What do we take the error? We take y minus y hat. Okay, y hat minus y. Okay, and then I multiply it with minus of x1. Okay, and this is not very intuitive. You will not understand why it is happening, but I will tell you now why it is happening. Since we have gradient descent here, okay, just note down this portion. This is a derivative of loss function with respect to one weight. Now if I have a function y is equal to m1 x1 plus m2 into x2 plus b, what do you think I will get if I differentiate this function with respect to m1? Since every other term in partial differentiation is considered as constant, this part will automatically become 0, since derivative of a constant is nothing. It is a parallel line to the axis which we are taking the derivative. With respect to m1, if I now differentiate, I will get x1. Okay, and since this order is not correct, I will do it like this: y minus y hat into minus of x. This order is correct. So when I differentiate it with this, and I have see, where do I find that gradient descent?
Satish, have you accidentally on put your video on?
So you see here why I'm multiplying this with minus x1, because when I differentiate it with m1, I get x1 as the uh, out residual factor. Okay, when I get the x1 as residual factor, I'll, okay, yes, I will know. I can see that it is still shared. Okay, so the loss function is j theta. Okay, so I'll just call it j. It is given for like y minus y hat square summed over all the examples. Okay, so when I have this as the loss function, I will differentiate this with respect to one of the weight with one of the weight m1. Where do I have this m1? It is hidden in y hat. How it is hidden in y hat? Y minus m1 x1 minus m2 x2
So, Prasoon, what you are thinking? You are thinking of deriving the equation for gradient descent, is it? The
Uh,
cost function actually, cost function you are doing.
I'm telling you why I have multiplied it with minus x1. You can
Okay.
do it with plus x1 as well, but I have used minus x1. Why I have used it? Because I am subtracting y. I'm subtracting this y hat from y. Okay.
So you are reducing value of y. You are going down the. You are decreasing value of y, is it?
Yes. I'm trying to get the error,
Ah.
multiply it with the feature for which I want to iterate the weight. I want to get the weight. Okay.
So right now you are going down, right? Once you go down and then if errors start increasing, I mean, first you are assuming that error will decrease, right?
First, no, this is still I'm still not going down, but this is about getting the weight.
Ah, okay.
When I will go down, I will tell you when I will go down. I will go down by the time I am there. Uh, what can I say? When I'm calculating these values.
Mm-hmm.
Okay. When I'm calculating these values, then you can say yes, I am going down. But for these, I'm just finding the next set of weights for which I will get a lower error value.
Mm-hmm.
Okay.
Right.
So, so
And you will keep iterating unless you sort of,
and these values don't change. These
much.
values are kind of constant or very slight changes are there. Or
Ah,
maybe I have a threshold of iteration, say 10,000 iterations are crossed and I do not reach any conversion.
okay. And then you will finalize on the weights, okay? And
Then I
then
will finalize on the weights.
from that you will uh, why this thing came in, because after that you will go towards regularization, right? After that.
Yes, after that I will because this is a very simple thing and the topic the data set which I just made at random will not converge,
Ah.
right? It is very I tried to do it, but it's not converging in very one, two, three, four steps are already done, right? But it is not converging.
Because you have done because it is random, no?
It is
You
very
have taken.
random.
Yes,
Yeah,
yes.
it's random chance. Okay.
Yes.
And then what we will do is why we will do the regularization is because we need to make it stop. Make it stop. How? See, these values, these will keep on reducing or these will keep on increasing. So to an extent, if this will bring it to 1 and this will bring it to 0, this might get you a very perfect model for the training data, right? This will give you a very perfect model for the training data. However, when you give it an unseen data, it will not be able to predict anything. It will just give you a random. It will throw you a random out class.
B does not need to be zero. B can be any value. I think you
It
mean
can
only
be,
M1 and
but
M.
it will try to. I told you na this formula is generalized over sum of W I
Acha.
to X I. This
So
is the
you don't have intercept term there, is it? Okay.
no. That is used in OLS. B is used in OLS. So this is generalized. So you will have one x1, you will have one x2. For x1 also you will get a weight. For x2 also you will get a weight. Okay. So these are the weights, and this is the bias, which can be for any single column. It will add a single column to your data, which is one, and then it will start getting values. So it can be zero, it can be point 0.1, it can be it can be 10.
So soon I get it. I mean, you are slowly building up that understanding. and we want to show that if we don't do regularization, probably there are chances of some of the of this sort of getting overfitted or underfitted, and you want
Yes,
to show that if a regularization is done, then it becomes more generalized. Am I right?
yes, yes, yes. And in addition to that, how do we come to this thing? You see this plot. I mean, I'm sure you guys can see my screen. I've shared the screen, right?
Yes, 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 yes.
Okay. So P norms. Why I said about the Euclidean space, Cartesian space. Why I told you about this norm is basically uh, suppose a vector. Say you are traveling in a plane. You are at a height of say 5,000 feet. Suppose, okay, and you are traveling in through some say turbulence. Okay, so there are variations. Like the movement is not very smooth. You are not in a linear direction. You have turbulence, and then your path has noise. It is shaky, right? So how do you pinpoint your location in that? You won't be able to do that, right? You won't be able to map it in a graph in a very smooth manner. Am I correct? Can you visualize that? I mean, you're traveling somewhere, you have turbulence, or maybe you are on a bike on a very bad road. You won't be able to take a very linear path. There will be noise to it, right?
Yep. Right. Right.
Okay. So added these noise is our daily life. Whatever we do, whatever we um, uh, uh, like live through our daily life, we have noise. We don't have a perfect data to anything. Every data we generate, we are eating, we may be working, we are using our smartphones, we have our smart wearables. Everything is generating data and has the noise, immense noise. So there is no way to generalize things so far. So what does this do? These norms. What does the norm do? They will give you a generalized sense of the importance of those features. I may not be able to communicate properly. I will need your assurance if you have understood this. What I'm trying to tell you. Say you have a feature X, X1, X2, X3. This will predict. These are X-rays. Okay, suppose X-rays of a person, and this will predict whether the person has cancer or not. Okay, these are X1, X2, X3. This class will tell you if whether a person has cancer or not. Internally, a person has many things, many other symptoms which might mimic their condition of say if there is a black spot or there might be a white spot which might mimic as a tumor, which might be then we'll have to go for CT scan and all, right? You get the idea that these features alone cannot tell you whether a person has cancer or not. However, these features are used these features are used in actual to predict the class whether the person has cancer or not. Correct? I need some confirmation because I'm trying. I'm sorry, but I need information, right? So these features will be used to predict the class, and these features are not perfect. Then how can we rely on these features? How can we rely is by using the P norm. How can we use the P norm? The norm is since these features are may or may not be linear also, right? This feature x2 might be dependent on x1, say quadratically or say cubically. It might be relevant, right? But those weights are always linear. Okay, these weights will always be linear, and We will take the norms of these weights only. When we start data science machine learning algorithms, we know for the first chapter is linear regression, and for linear regression we have IID. Every individual feature must be independent. Okay, and if it is not independent, we don't have any problem because these parameters are linear and independent, right? And we find the norm just to get the generalized idea of the error, right? just just note it down. You'll have some time to absorb this will take some time to absorb, but just note down that this will generalize the weight. The idea of these weights is generalized using a norm. One norm will give you lasso, two norms will give you a ridge regression. Okay, now here we see a 2D plot, a 2D plot of W1 and W2. And how are we going to visualize it? We are going to visualize this in terms of norms.
There is
This
some background noise. Has anyone by mistake?
Mr.
Uh,
Tiwari has his mic open now. That's why. There's no issue. Like
no, if someone who Manoj, can you mute Mr. Ishwar Tiwari?
okay, okay. So guys, yeah. So in P norms we have P equal to 1.
Uh,
How?
Prasoon, do you mind if I sort of butt in?
Yeah, yeah, please, please.
I think by the silence of the audience, by
Hmm.
gazing, I can understand that this topic is pretty dense,
Yeah,
right?
it is.
It is dense, and people probably need some time to wrap their head around it.
Of course,
Hmm?
even I have so many doubts regarding the computation part that
Hmm.
even I cannot wrap it up in one session because it's very overwhelming topic. I told Manoj before also. It's very overwhelming topic.
So, are these presentations you have created presentations, or
No,
is
no,
it
no, no, no. These are curated presentations. I did not even find a single visualization that can
okay?
tell what my intuition. No.
So, if if all the people here are sort of are on the same page, let me propose something so that this discussion becomes a bit more fruitful.
Yeah, please, please. Yeah.
So, I would say we have not, I think, recorded it. But if there is possibility of sort of covering up the salient features of it, right? If you can make some pointers or some videos how to understand, because this is very important topic, right? And the kind of approach you have taken, which is mathematical, is the probably only way to understand this. Otherwise people will remain superficially there will be superficial understanding of it. Okay, so is there possibility if you point wise give some pointer, or uh, I think we have not recorded, Manoj. We have not recorded this session, right? We are recording. Okay, we can sort of make it open also, and you also, if spare some time and make some document out of it, which
Mhm.
can be sort of uh, though all of us are we have done your RMFDS, and we have done second semester also, but many of us might find it very very difficult to follow. Okay,
Okay.
so
Mhm.
if there is a possibility of putting it in a layman term, right, circulate it, and before we start it again in the next session,
Mhm.
people who are who sort of interested, as well as who want to know more about it, they can come prepared.
Yeah, of course. I wanted to, give it a heads up yesterday itself, but I thought maybe I can start with
So
this.
this is important. I mean, I think approach you have taken, sort of impresses upon people that it is not a very sort of cakewalk. It's
No,
sort of,
it is
yeah.
not. I have tough time in calculating and how the CPU manages to calculate the gradient descent in so
Hmm.
efficient manner, because our precision, the number system which we are using is IEEE 754, and it doesn't have this capacity to wrap around those float points of 32 bits.
Yes.
Um,
So, so if it makes sense to you, Prasoon, can we should we take that path? What we post, probably put some pointers somewhere in document, and
mhm,
sort of or this presentation, whatever you think, whatever you have sort of excuse me, completed till P norms,
mhm,
right? And
mhm.
how they are going to help us in generalizing,
Yeah.
right?
Okay.
till
Okay.
till that point, if you can sort of create some material, share with us, we will be much more prepared when you sort of go ahead, and how from P norms to regularization, how this works. This will be much more sort of I think participative.
Okay. 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 Done. Done. Done.
What do you think?
I'm okay with it. I will have to make some pointers, but I'll try to make some good notes on it. If
Yeah.
possible, if I could not make it in like PPT or something, I'll try to make it write it down with my own hand, and then I'll paste it in a
Yes,
Word,
yes.
like I just shared this one.
I think that will and people people will have some time. Yeah, yeah. Like, please share this also, whatever you have prepared this way, right? And people sort of people will have some time, and probably give it 2 3 days, right?
Hmm.
And
Hmm.
all of us come prepared with whatever gone through, and what you're going to achieve, which is create understanding of regularization. Uh,
Hmm.
that will be, I think, much more fruitful. That's what I
Yeah.
think.
Okay.
Manoj,
Yeah.
what do you say?
Sounds good. Yeah, I am there. Which one, sir? Yes, yes. I searched for it for from the books and from other authors which they have used, and they have said like it will be very required, because in artificial intelligence, you guys don't have artificial intelligence in the last semester, right? Manoj, you don't have. But since artificial intelligence course asked us to solve some pretty good problems, and these algorithms were not very I did not had it in my mind. I did not learn them by heart. These would have been very easy for me to write the codes if I had known these basic data structures used back then. So yeah, that's why I just noted down all this, that I have to learn all this. Yeah, yeah, okay, okay. I'll share this, and I'll make some pointers as well. I tried to make this PDF kind of thing, but I am not yet done, because I was studying about trimality testing, which is used in this is the basics, but there's so much of topic I still need to cover. Anyways, if you
studied, were taught by the teachers.
No, no, sir. These topics are you cannot curate this from one book, which I've understood so far. Earlier, I had this feeling that I might purchase these T1 or R1, R2 books, and then I will find the main intuition or motivation for all those concepts or algorithms which are being taught. But what I understood from data science, learning this data science so far, you cannot go with a single book. You do not have any single answer to any single problem. There are
Okay.
multiple ways, there are multiple sources, there are multiple avenues through which you can solve the problem, right? And it is all about notations. If you are a core hardcore mathematician, then it is very easy for you to write down things and solve things, because half of the job is done by the notation itself. But since we are not hardcore mathematicians, all our mathematics have are back to college days. Or since I am a mechanical engineer, I used to compute those strength of materials and heat dynamics. Okay, so my mathematics was till that. I don't know about you guys, but that was it. I did not come again revisit those mathematics concept ever again before starting data science for this. And it is so very overwhelming because just like you said, no, that 0 1 loss function, integer function, I used to skip those parts. I mean, it did not even register on my mind that I'm reading something which can be very much crucial. I just used to skip. Okay, someone must be there. Okay, this might be this function, this might be this reason, for that reason they have must have written. I should not go in deep. But once I started understanding the meaning, I knew that this function has so many applications, and by writing this, most of my understanding would be clear for the future, theorem proving or anything like that. So you cannot go for one single source. I'll suggest is every handout has these T1 books. You try to get the soft copies, keep it in one place, in one folder, or maybe buy them all. The best suggestion is to buy those books, because what you read from a hard copy is far better than what you read in soft copy. You can go up and down those pages, and you much faster on your approach. Then I'll tell you, you always sit with a marker with your books, highlighter. Any point which you think that you might not understand right now, just highlight it. You search it online. If you can take a chat gpt subscription, do it immediately. Chat gpt 4 will teach you everything related to algorithms. It will teach you, like, even the counting theorem, how the counting is done, the probability, how the posterior probability came into existence, why it has come, everything. So I'll just suggest buy those T1 books, get a chat gpt subscription, and study from every source, every topic in the. And yes, for these books, in the T1 books, you don't have exercises, solution exercises, but in some books they are given at the last. I realized it in the artificial intelligence subject. It was given in the last, the solution exercises. And if you are like stuck on some topics, you can of course use these references from other authors which these books use. Every book has these references in the backside, right? Where they give which topic is taken from which publisher and which author. So you can read those from the research papers. This will be very helpful. And yes, you will need the skill to read a research paper this semester itself. So please try to brush it up as well, because it is very crucial, and a research paper is not very easy to read. I'll just suggest you please look through it. And yeah, maybe this will help you, because I suffered a lot. I am suffering still, but this
Prasun, if you have any research paper, can you just share one?
research paper. Yes, I do. I'll share it in WhatsApp. I might have it because in the last ML assignment they gave us, no, a research paper.
Right.
Yeah, I'll share that. Don't worry. I'll share that in WhatsApp. Okay. Yes, Vinay sir, can you just please
Yes, yes. So I will, you know, do a very simple sort of. Can you see my screen?
yes.
Yes. Okay.